Now we are at the end of this chapter on multi-layer perceptrons. In this entire journey of this chapter, we went through a lot of components of multi-layer perceptron. And when we implemented the model, we had different choices. The choices included the number of layers, the size of the layer, the activation function, and so on. With these many choices, we get a lot of flexibility of building a very useful model, a very powerful model, but it can also be overwhelming sometimes. And it is very easy to get lost in between these many choices and eventually end up nowhere. Therefore, now we will look at a few rules of thumb that help you build a first model, a baseline model. These rules of thumb may not take you to the best model, but it will get you started, it will give you base. So, this is our MLP illustration. Let me start with the input X. We want to do a few data pre-processing before we ingest X into our model, and few necessary pre-processing on X is make it numeric. If you have any categorical columns, just do a hot encoding on them. Second is scale your X. Scaling is necessary because if the range of X is minus infinity to plus infinity, training this model becomes very difficult. So scaling is necessary. When we are scaling X, two good choices are either use standard scaler which scales the X into 0, 1 distribution, meaning the mean will become 0 and variance becomes 1. It is like normalizing the data. And the other good choice is min-max scalar. This is mu and this is sigma. Min-max scalar brings the data, each feature in your data between 0 to 1. So this is min and max for each of your feature. Between these two, which one to use? Again, rule of thumb is if your original feature is unbounded, meaning it is from minus infinity to plus infinity or 0 to infinity, any unbounded region, then use a standard scalar. And if it is bounded between any constant value, for example 0 to k, a good example is image data. In image data we have pixels, and those pixels, the value of those pixels are between 0 to 255. In such data, it is good to use min-max scalar. After this, you want to split the data into train, valid, and test sets. We'll use a training set for training. Valid will be also used during the training, but only for evaluating the model on a different held out set, valid data set, validation data set. And test is once you have tried a variety of models, you select the best model using their performance on the validation set, and finally whichever you have selected you apply it on test set. This should be done only once to report what is the expected performance or accuracy of your model. Remember, you should not apply all the variety of models you are developing on the test set, and based on that make a selection. Because if you do that, if you make a selection on the test set, you are again overfitting. Unknowingly, you are overfitting your model on the test data. So bring test set only when you have finalized the model and apply it only once to report the performance. Next, we'll move to the layers. The size of the layer is, before I get to the size of the layer, the number of layers. The number of layers in the baseline model, it is good to start with 2 hidden layers. Two hidden layers and 1 output layer, as shown here. 2 hidden layers, 1 output layer. Hidden layer 1, hidden layer 2, and output. Okay. The size of these layers, the size of the output layer is determined by the size of y. If it is a binary classifier, meaning y can take only 0 or 1 value, then the size is 1. Also, if it is a simple regression model and which has only one response y, it is still same size of 1. But its size will be equal to k if suppose you have a multi-class classifier which has k classes. Or if we are doing regression and if it has k different responses, then you still keep the size of output layer as k. In the example we used in this chapter, we had a binary classifier, so our output layer was of size 1. About the hidden layers, the size of hidden layer, you can choose it from the geometric series of 2, which is series like this. From this series, take the number which is closest to half the number of features that is coming as an input to this layer. For example, if my X has P features in the first hidden layer, I will be closest to P by 2, the number that is closest to P by 2 in this series. In the second layer, I will take the size of half of the previous layer, because this is already in this series of geometric series of 2. This will automatically be also in this series. Again, this is to build a baseline model based on few rules of thumb. After you have done that, then you can optimize on top of this. Next comes the activation. As a rule of thumb, use the activation ReLU on all of your hidden layers, and on the output layer, the activation depends on your response again. If you are building a classifier, you want to use a sigmoid activation. Sigmoid has an output in 0 to 1, which is what you want in a classifier model. If you had a multi-class classifier, then a extension of sigmoid for multi-class becomes a softmax function. You can use a softmax activation function. And if you are not dealing with classification problem, if you are dealing with regression problem, the activation here should be linear. So this is for regression and these two are for classification. Then we have dropout, which is very common, but in baseline model, I prefer to not add dropout. After we have built a baseline, then we add dropout to see if it improves the model, and if it doesn't, then we increase the size of the model and then again apply dropout and iterate from there to get to a best setting. So far, we learned a few rules of thumb to construct the model. Now we are at the stage of model compile and fit, starting with model compile. One necessary argument in the compile is optimizer, and as a rule of thumb, we should use the Adam optimizer. Among all the choices that we have, Adam optimizer is most robust to the hyperparameters. It's insensitive to them. That makes it easier to get a baseline model ready quickly. We can use Adam optimizer with its default learning rate and other hyperparameters. Next is the loss function. If we are dealing with a classifier, then we should use cross entropy. If it is regression, then MSE as rule of thumb. Again, if it is multi-class classifier, then we can use categorical or sparse cross entropy, otherwise simple binary cross entropy for a binary classifier. Then we have metrics. Now, depending on the problem, metrics differ. Here we were dealing with a rare event prediction for which we defined special metrics. They were recall, F1 score, and false positive rate. This rule of thumb is valid for rare event prediction when there's extreme imbalance in the data. If you are working on regular problem, then if it is a classifier, then you can use simple accuracy. And if it is a regression problem, you can use MSE. And then coming to the model fit. The two important arguments in model fit is epochs. I generally prefer starting with a few epochs, like 5 or 10, and if in that I do a sanity check on my model, if my accuracy measures and loss function look to behave normally, then I go forward and try an epoch of 100. The thing with epochs is it's hard to know ahead. The way to see whether your epochs is set correctly or not is run the model for example 100 epoch and look at your loss function and accuracy metrics. If your loss function has stabilized, like it has decreased and stabilized, you are good. But if your loss function is still fluctuating, not stabilized, then you want to go for more epochs. Another thing, you can start relearning the model from where you left. So maybe if you learned the model until 100 epochs, you can restart the learning. You can again run the fit function in TensorFlow for say 50 epochs, it would mean you are doing the learning from epoch 101 to 150. And another argument in model fit is the batch size. The model learning is not much sensitive to minor differences in the batch size, just like here for the hidden layer size. Therefore, we can also choose the batch size from this geometric series of 2. It also depends on the problem. For a rare event problem, I selected the batch size to be 128. This is keeping in mind that if I set the batch size to be too small, since my data is extremely imbalanced, it is likely that the batch that goes in the model training has no positive labeled data, which is not good for the learning. Therefore, I keep the batch size large enough that reduces the chance of that happening. If you increase the batch size, the model learning reduces, but the model learning is more stable, and vice versa. If you reduce the batch size, model learning is faster, but it may be noisy. And another argument that we have is class weights. Class weights are used for imbalanced data sets to give more weight to your minority class, but class weight does not work very well for extremely imbalanced data like ours in rare event prediction. Therefore, it is good to avoid class weight unless really necessary. And lastly, before we go, a few guidelines on some of the issues we can not commonly, but sometimes find when we are training our model. That is oscillating loss. Oscillating loss means my loss is coming down, but then it goes up, down, up, down. Sometimes the model oscillates. This is loss. And this is epochs. When I have the oscillating loss issue, you can do two things. And I'll use a different color here. Reduce your learning rate. This you can do here, or change the batch size. This you can do here. Another thing that is specific to the event prediction problem in time series is do not use oversampling methods, including advanced methods like SMOT. They do not work very well for oversampling. Does not work very well for extremely imbalanced data set like a rare event problem, and SMOT does not work for time series problems. And this is for extreme imbalance. They do not work for this. With this rules of thumb, we conclude our chapter on multi-layer perceptrons. We'll meet again to learn about long and short-term networks or LSTM networks in our next chapter.